Hello everyone, welcome to the next video installment of design of synchronous machine. This is video number 4 from the ongoing series of solved numerical examples from the subject electrical machine design and from the unit of design of synchronous machine. In this video lecture, I am just going to explain a very important numerical example for your exam point of view, whether it is your competitive exam or your RGPB university exam. The numerical is on the screen, which is determine the main dimensions of a 75 MBA 13.8 kV 50 Hz 62.5 rpm 3-phase star connected alternator. Also find the number of stator slots, conductors per slot, conductor area, and work out the winding details. The peripheral speed should be less than 40 meter per second. This is the condition given for you, that the peripheral speed must be lesser than 40 meter per second. We have to ensure this. Assume average gap density as 0.65 Weber per meter square and a specific electric loading as 40,000 ampere conductors per meter and current density as 4 ampere per mm square. Now, before going to the solution, I always used to advise my student that whenever dealing with long answer type questions, it is always necessary and advisable and in favor of us to read that questions at least for 2 times or 3 times. Basically, if it is numerical, if you'll read that numerical example questions statement for 2 times or 3 times, you will get the idea that what has been given to us and what has been asked by us, and you have already gone through the concept. You can actually correlate between these 3 things and you can start the numerical in the right direction. However, just I'm starting the solution. Here it is. The synchronous speed, I'm converting from RPM to RPS, dividing it by 60. 62.5 divided by 60 is equal to 1.0417 RPS. And the number of slots, number of poles is equal to 120 F by NS. This is from the popular formula, synchronous speed N is equal to 120 F by P. So the P is equal to 120 F by NS. 120 into 50 upon 62.5, that is 96. And the winding factor, we have to choose the winding factors. We know the winding factor is 0.955. As a design engineer, you should keep in mind that winding factor is 0.955 or in between this range. We know output coefficient C node is equal to 11 BAV Q kW into 10 to the power minus 3. BAV is your specific magnetic loading, Q is your specific electric loading, kW is your winding factor we just discussed now, which we have chosen 0.955. Put the values and calculate. It is 273. Now calculating the main dimension of the machine, that is capital D and capital L, from the formula D square L is equal to Q upon C0 NS. Put the value, you will get the combined D square L is equal to 264 meter cube. Now it is given to you that the peripheral speed must not be greater than 40 meter per second, or it should be lesser than 40 meter per second. The boundary is given to you for the peripheral speed. The formula peripheral speed is pi d ns upon 60. Put the values. From this you can calculate capital D. Once capital D is calculated, the capital L will automatically be calculated. 1.77 meter is the value of capital L. Now pole pitch is equal to pi dp means pi d upon p is equal to pi into 12.2 upon 96, that is 0.4. We also know the relationship for flux per pole is equal to BAV into pi dl upon p. Put the values, calculate, it is flux coming, it is 0.46 Weber. E phase is equal to 13,800 upon root 3. It is coming 7,960 volts. Now let us assume one circuit per phase. So turns per phase TPH is equal to EPH upon 4.44 F 5 kW. Put the values, it is coming approximately 82. As the terminal voltage of the machine is 13.8 kV, slot pitch of about 5.5 cm should be used. Hence the number of slot is equal to pi d upon tau s, pi into 12.2 into 100 divided by 5.5. This is your slot pitch which we have taken. So the number of slots per pole per phase is equal to S upon 3P is equal to 696 upon 3 into 96. It is 2.42, which is a fractional number. Note this result, number of slots per pole per phase. In a phase, in a slot, what is the number of slots per pole under a single phase? It is 2.42, which is fractional. That means the above fractional value of slots per pole per phase indicates that fractional slot winding is used. It is clear? So number of slots and turns per phase must be finalized such that they should not differ significantly from the earlier calculated values. So it is also to be noted that for fractional slot winding, double layer winding is a must, and hence conductors per slot must be an even. Assuming number of slots per pole per phase as 2.5, actually it was 2.42. I am here assuming it is 2.5. It is still a fractional. So total number of slots will be equal to 2.25 into 3 into 96 is equal to 648. Therefore total number of conductors is equal to 2 into 3 into TPH is equal to 6 into 82 is equal to 492. Hence number of conductors per slot is equal to 492 divided by 648. It is the total number of conductors divided by total number of slots. We want to calculate number of slots per slot, number of conductors per slot. So it is total number of slots divided by it is total number of conductors divided by total number of slots. 492 divided by 648, which is coming as fraction. Hence a double layer winding is not possible with one circuit per phase. It is obviously clear from this statement, above statement, which is coming fraction. Hence the number of circuit is to be selected in such a way that number of conductors per slot is even number, and the winding becomes symmetrical. Winding must become symmetrical. It cannot have 1.5 winding or 1.13 winding or 1.21 winding. Taking the number parallel circuit as A is equal to 8. A represents number of parallel paths or number of parallel circuit. So just take A is equal to 8, which is a even number. So turns per phase TP is equal to A into EPH divided by 4.44 F 5 kW. You can take A is equal to 16 also, or 4 also, or 6 also. Just for your knowledge, you can calculate by keeping A is equal to 6 or 10 or 12. I have taken here A is equal to 8. Let's see what the result is. Hence total number of conductors is coming 2 into 3 into TPH, 6 into 654. 654 was your turns per phase. It was approximate number 654. So the total number of conductors is coming 3924. Therefore, number of conductors per slot will be equal to 3924 divided by 648, approximately 6. So it is okay. Hence the number of conductors is equal to 6 into 648. It is 3888. Hence turns per phase TPH is equal to 3888 divided by 6, that is 648. And the current per phase is equal to 75,000 into 10 raised to power 3 divided by 3 into 7960, that is 3140 amperes. Current in each conductor is equal to current per parallel path, which is 3140 divided by 8. 8 was your parallel path and 3140 is the total amperes coming. The result is 392.5 amperes. Now the area of cross section of each conductor is 392.5 upon 4. It is coming 98.125 mm square. Area of cross section of conductor being very large, conductors are stranded and used. You can see from the numeric values that area of cross section of conductor being very large, so conductors are stranded and then used. This is the complete detailed solution of numerical number 6. I am giving you numerical number 7, another example. Just you can try it, or you can see how it is related to the topics taught to you. I'll be coming with the detailed explanation and solution of this numerical example number 7 in my next video. Till then, thank you so much.